Okay, today I thought we'd just play around with some different gearboxes from my junk box room that show different ways of doing mechanical sequencing. Some using cams, some using the rotating lever type mechanism like in the Rotomatics. So you might find it interesting. Take a peek at some of these things. To power them, I've just grabbed, and I guess it's kind of off screen. Grabbed a couple old junk battery boxes out of toys and wired them together in different configurations so I can get anything from 1.5 volts, 3 volts, and 4.5 volts, whatever's required. And in this case I thought we'd just start with this. This is a large bump and go drive, but you can see what's weird about it is you got this big green box and you've got this big box up here and you're going, what the heck is all of that? Well, this is some of the guts from one of the Gang of Five, the Sonic robot, better known to most collectors as Train Robot. Sonic Robot was sold in basically two different forms. The most common one has this fan blown. This is a fan. This is a whistle. And it would make train type sounds. The other version, instead of the train whistle, actually has a slide whistle, and it made more sonic sounds. So that's the name Sonic Robot. The Sonic one is more rare. This is the train version, and the toy would operate on 3D cells, so that's 4.5 volts. And that's what we've got here. And let's power this up. So, what this is an example of is a cam being used to do sequencing. Whenever this lever is lifted, see it'll make the whistle work by letting air get in or blocking the air from the whistle. This lever that's sticking up here, this was used to control arm movements and stuff like that. The cam that's actually causing this to happen is down in here, and I don't know if the camera's picking that little cam up or not. It's not very big. It's got lobes on it, and it comes around. And so this is one way of doing a sequenced effect mechanically. Now another way, still using a cam, and I haven't powered this up, and if I power it up the wrong way it'll jam up, but we'll find out. And this should be running on 3 volts, not 4.5, so let me move a few wires. Let's see if we can get 3 volts into this thing. Okay, we're going to be running the right way. So in the case of this toy, here's the cam. You got your motor, and you have to gear it down and gear it down and gear it down, and then even after that gear, deep inside that hole in there, there's a worm gear that drives this gear, gears it down even more, so you can get a very slow RPM on this cam and a lot of pressure. And when that cam can move, it can lift this lever, and that lifts this gear. Now lifting that gear is going to do a couple of things. One, when the gear is down, it engages here, which is the bump and go drive. But when it's up, it would engage a whole another function. This is like what would be used in the Chief Robot Man. Also sold under the name Moon Robot and Radical Robot and stuff like that. So here comes the cam. It's lifted the gear up, so now you see we have motion up here on top. And now it's dropped down, so now we have motion for the bump and go drive down below. And a cam like this can be set to do more than just a simple on. It's doing this and then off. The nice thing about a cam like this, and this one's been modified, there would have been a second lobe there. They actually not only had this long duration, but then a short one, so it could momentarily drive the up one, then go back a bump and go drive, then come back around and do the long one in the bump and go drive. So that's another way of doing mechanical sequencing. Let's take a look at Well, one of the more familiar ones, I guess. This is kind of the motor drive out of a standard, fairly standard, Rotomatic type robot. And that's what happens when you hook the power up backwards. The rotating wedge will jam. So let's make sure we get the power connected up the right way. Okay. We've got the two spinning gears here, and they've got... I'm going to stop and give you a better breakdown here when this thing lifts. I'm going to pull the power. What's really unique about the rotating lever shifting system, basically all it's trying to do is take this shaft and raise and lower it on sequence by a ramp that separates the two gears, which is what moves the shaft up and down. There's a return spring there. But what's unique about it, other than that, is that you don't need all of this gear reduction. You got 1, 2, 3, 4, 5. How many steps of gear reduction you needed to get to about the same amount of time period to do that is by just having these two large gears, and one of them is just one tooth different than the other. That gives you a gear reduction right there. For example, if these had 20 teeth on them, but this one had 19, it's got to go around that 20 to 1 in order for that ramp to come up and down. Now granted, depending how long you want it to be in the ramp up mode and the ramp down mode, you then divide that in half. But the whole point is, by using a whole lot less moving parts, less gears, less money, you can still get your sequencing effect in a smaller area, in a much simpler design. So basically you have a motor here, gear reduction, turning this large brass gear, large in that it's long, so that it can engage these two gears, which have a different number of teeth on them. Usually it's only one tooth difference, because that gives them more of a reduction. And then you've got a slot. Now you don't have a slot in all of them. You just do in the majority of these. In fact, let me show you another example of this that doesn't have the slot so you can understand better. This is out of one of the larger Rotomatics, like the giant robots and those kind. So instead of putting a slot into the two gears that have a different number of teeth, they build a metal wedge, if we can get the lighting right. See that wedge? And the ramp, which you can see here, crawls up the wedge, and when it gets all the way to the other side of the wedge, then it drops down. So right now, let's, again, if I get the power hooked up wrong, things will jam up. But I can't remember which way is which. And that's obviously the wrong way, so let's try this way. You got to make sure you get the power right on these rotating wedge types. So this one's going to move this shaft up and down when it crawls up that wedge. And normally this actually would be running on 4.5 volts. So now it's separated. I'm going to stop it where it's separated so you can see that. See that wedge? It's up on top this block now. In fact, let's rotate it. See, the block is just made out of folded metal, which is crimped right onto that gear. And it crawled up. And when it gets all the way over to this side, the wedge crawls all the way over here, it's just going to drop off and they're going to go down. Now the unique thing that I wanted to show you about this was, in most of the Rotomatics, you know how they sit there and chatter and the doors are open. Well, the chattering is actually normally done because when it's reached the extreme for the body rotation and the guns to go out, the gear that's doing all of that is literally hitting the last tooth on the gear that's causing the Rotomatic and the door to open, and just sitting there hitting it, bang, 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 bang. And what that does is, it wears the soft tooth off that last gear, and it also wears a big groove into the brass gear, so it can't last very long. What they did on these large Rotomatics, so that because there's so much bulk, or so much more mass, is they got more clever about it. They actually cut a slot into this gear, as you can see right there. And when the gear crawls all the way around, it drops down into that slot because this gear is set on a spring. Spring's right here, pulling it towards it. So it's sitting there and it smoothly rotates. No chattering, no wearing of that brass gear. Then when it comes back, this spring returns this whole piece. When the gear comes up, see that's bent on purpose, factory bend. When this gear comes up, watch it engage, crawls around, drops right into its happy slot. This would have opened the doors. The clicking would be from this triangular shaped piece here. As this came around, there'd have been a big clicker that would hit that, so the guns would make a big clicking sound. This, of course, would go on down into the walking. So right now it would be walking, and there it has moved away from the walking gear, so it stops walking. Doors go open, rotomatic, all that good kind of stuff happens. So they did have designs that could last and weren't basically self-destructing themselves like most of the small rotomatics were. Here's another example. It's really nothing new. This is basically the guts, and again, let's find out what direction's what on this. Let me power this thing up here and let's see if things jam up or if they work. They jammed up, so let's move these two wires around. These are the guts out of a Repro smoking robot, the large tin one. And down in there you have the wedge. If we can add a little bit more light here. See if that helps at all. So you're in walk mode now because you can see the leg cranks are moving. Then it closed in, so right now you're actually in the smoking mode, and now you're back into the walking mode. Nothing really new about that. It's just instead of rotating or moving guns in and out, in this case they were stopping the walk action, enabling this gear drive, which could hit this little lever up here. See that lever? The smoker would have mounted up here, and every time this came around, it would push the smoker bellows up and down. Just one more thing. Then I saw this just laying out there for the fun of it, and I thought, yeah, maybe some of you guys have never seen those mystery boxes. Basically, the Thing from the Addams Family inspired this toy, and it's where you put the coin in, then a hand comes out of the box, grabs the coin, and then it turns back off again. I don't remember if this was designed to run on 1.5 volts or if it was designed to run on more. Let's try 1.5 and see if it even runs. But even beyond that, we've got to try to make the motor connections. And I think I may have to cheat since we don't have the coin holding part. That doesn't seem to be doing anything for wanting to make it run. I don't even know if the motor in this thing runs. Just pulled it out of the junk room, so you just never know. Let's move a few of these wires around. I'm going to get it with 3 volts. Because either it would have ran on a single cell or it would have ran on 2 cells. And we're not getting any motor action out of it, and the way it's designed, it's almost impossible to get in to the motor. Really needs a wire put on this contact to the motor right here. Let's see if we can get any life to come out of it. I'm not really getting any life to come out of it. That looks like a split gear anyway. So even if I'd gotten this one to run, because that gear right there is split and needs to be replaced, the motor would have just sat there and twirled and done nothing. I could probably get the motor to run because the nice thing about it is I can get to the brushes down here. These 2 tabs. Can lift that out, get in there, clean the brushes, see if they're broken, what kind of condition they're in. But what I was going to show here is not only the sequence of it moving the arm to come up, but how it turns itself back off. Is it has an electrical switch right here and a wiper. And what happens is when the coin is initially bridged across here, the coin forms a switch, supplies the power to the motor, so the motor starts running and the hand will come all the way up and can grab around the coin, no problem. But you're going, well, when it pulls the coin a little bit away, what keeps the motor running long enough for it to complete the cycle? And that would be this metal cam right here and this metal wiper. Because once it started running, those two connect, and that's what's then, you can, initially if you start the toy, you can take the coin away and it'll keep running because it's going to get its power through this switch cam down here, and it'll continue to run all the way until it drops down into the slot that it's sitting in right now. Then the power will be removed from the motor and it'll stop. So it's actually a rather ingenious mechanism. It's just a friction fit on the hand. Comes up, wedges around the coin, it's released, the spring pops it back into the box real fast, and this is part of the derailleur that's supposed to help knock the coin out of the hand. The coin should land down on this ramp down in here, and with any luck, the next time the hand comes up, if the coin is still sitting down in that ramp area, the next time the hand comes up, the coin would get dumped down here and end up in the bottom of the box. But looks like it needs not only a gear replacement, but a little bit of work on the motor brushes. You know, we can always try just spraying some contact cleaner in on the motor and see if we can get things lubed up. But like I say, without that gear replacement, it doesn't really matter a whole lot whether we lube things up or not, because the motor isn't going to really take off and go. I can get to the back side of the motor here too, which probably would need, ooh, almost heard a little something going on there. Can barely get my fingers on there. Now, this one's going to need a little bit more tender love and care to get going. I just thought it was interesting, and maybe a lot of you hadn't ever seen the insides of the old thing coin boxes. And they made, of course, a lot of different versions of them through the years, large ones, small ones. This is one of the earliest ones right here. So there you have it. I'm just having some fun with the mechanical motor-driven sequencers. Basically the rotating wedge versus straight out cam control.